Welcome back. We are talking about wastewater treatment, under which we are discussing the different options for secondary treatment. Now, this is the activated sludge process, and wherein we are discussing about that why the sludge should be recycled back into the aeration tank to improve the process efficiency and to retain the active life of the biological solids into the system. We are recycling the wastewater, and that will improve the process efficiency for the BOD removal in the tank. So now we'll come across with one particular term that's called MLSs, mixed liquor suspended solids. That is nothing but the composite mixture of the solids which are present in the aeration tank after recycling. Initial solids are X naught, and the concentration of the solids is XR. When these two are now mixed here in the tank, they're having a consistent concentration of X. There is nothing but mixed liquor suspended solids or MLSs. What does this consist of? That we look into here. So mixed liquor suspended solids is nothing but a mixture of solids entering into aeration tank and recycled sludge in the aeration tank. So its composition, it can be written as X is the MLSS is equal to XM plus X1 plus X2 plus X3. XM is nothing but a mixed liquor volatile suspended solids. That means organic fraction of the MLSS. MLSS can consist of inorganic as well as inorganic. So there mixed liquor volatile solids is nothing but the organic fraction of that, which is around 80% of the MLSs. X1 is the active microbial mass, milligram per liter of VNSS, and X2 is the endogenous respiration mass, milligram per liter of VSS. VSS means nothing but volatile suspended solids. Inert non-biodegradable organic suspended solids, this is milligram per liter of VSS. So ultimately, the entire biological decomposition is mainly taking place of the organic solids. So MLVSS use a representative fraction of MLSS. So MLVSS value is generally considered in all the calculations rather than MLSS. Now let us look at the another term which is also used in the treatment systems of ASP, soluble BOD. There is a 5-day BOD and then again soluble BOD. Soluble BOD is the difference, is any difference between soluble BOD and BOD5? We'll look at it. BOD5 represents oxygen demand by most common wastewater components such as the sugars, fatty acids, and starches. The matter remaining after 5 days in the BOD bottle can be assumed to be insoluble. Whatever the soluble material is there is now already undergone in the decomposition during the first 5 days. That's what we are now calculating in the terms of BOD5. So that's why BOD5 can hence be referred to as insoluble BOD. Okay. So now here the ASP mechanism settled was now treated in the process. So it can be assumed as the influent soluble BOD as S0, and it is also equal to influent BOD5. So we are talking about only acetyl waste in the treatment of the process. So here soluble BOD, which is nothing but BOD5, it can be assumed to be same as influent soluble BOD. So both are similar portions. And but effluent solids basically coming out from the secondary treatment system consisting of both biological solids plus soluble organics. Biological solids are now going through some recycle, or maybe they are escaping from the system. Soluble organics are there, and they are also there in the system. So now effluent soluble BOD SE should be approximated to detect the biological cells leaving the system, because we want soluble effluent BOD, that is again having some biological solids component also into that. So this is what we are trying to calculate by having an empirical formula. SE is equal to effluent BOD5 minus 0.63 times TSS leaving. So TSS leaving is XE value. So LE minus 0.63 XE is equal to the S is soluble effluent BOD. So the assumption is here BOD5 is similar to that of soluble BOD. So S naught is can be considered as a L naught, but SE soluble effluent BOD is now to be calculated based on this empirical relation, so that the efficiency of the process is based on soluble BOD. We can calculate as S naught minus SE by S naught into 100. So based on this soluble BOD concept, some growth rate equations are there. In the complete mix process, so to find out the microbial mass in the reactor, that is nothing but X, where MLVSS is there. So now we will write down the equation as SRT by HRT into Y into S naught minus SE divided by 1 plus KD into SRT. So HRT is nothing but V by Q. So using that value here, if I replace this HRT is V by Q, YQ by V into SRT into S naught minus SC by 1 plus KD SRT. Then what is Y here? Y is nothing but growth yield coefficient, which is nothing but mass of the cells formed by mass of substrate consumed. What is the efficiency of the conversion? And S naught and SE is nothing but influent and effluent soluble BOD. HRT is equal to V by Q hydraulic retention time. SRT is solid retention time. KD is a decay coefficient of microorganisms expressed in terms of per day. So typical values of Y and KD, if you look at 20 centigrade, Y is equal to 0.4 to 0.8 milligrams of volatile suspended solids per milligrams of BOD5, typically around 0.6. KD is a decay coefficient, which is around 0.04 to 0.075 per day, which is around 0.06, a typical value. Now, other one, we are talking about complete mix process, solids retention time. How you are going to calculate this? We already discussed in the video, but still, any change in the definition? There is no change in the definition, but here that solids retention time is nothing but how much of the solids are which are retained in the system divided by how much solids are leaving through effluent cycle, how much solids are leaving through sludge cycle. The same thing we are writing. SRT is equal to Vx is the solids retained in the system, and something what is leaving from the effluent system, what is leaving from the sludge system, QWXR. The same SRT we are using in the equation to calculate the value of X. Same, now we are talking about the growth rate equations for plug flow process. In the plug flow process, the only thing is there is no complete mixing, only radial mixing. The lateral mixing is possible. And we're moving in the longitudinally in the tank. The wastewater is moving. There is only lateral movement or lateral spread or lateral mixing is done. Because of that, the concentration of the solids in the tank is now to be considered as average concentration at different points. That's the only thing you are talking here, the average microbial mass in the reactor. So we are writing as XA. So all the terms are same, but only difference is instead of single MLSS or MLVSS, we are having average microbial mass. All of the terms are same as per complete mix process. The same values of Y and KD are there. But here, in this case, SRT also you can see The same thing is there, but in this tank, what we're talking is the concentration of solids is now varying because of only this vertical mixing, not the complete mixing. So therefore, the average concentration of MLVSS or MLSS we are considering in this equation. And how much of sludge is produced per unit time in terms of MLVSS? We're going to calculate is change of solids concentration per change of time, dx by dt. That we can write down using the formula Qy into S naught minus SC divided by 1 plus Kd into SRT. So this is using this formula, we can calculate the sludge production per unit time in terms of MLVSS. So now the same information, we once again will talk here. This is the different types of processes and the design we talk about. This is the MLSS. Remember, this particular thing is the MLSS. And for the MLVSS, we assume 80% of this concentration. So in practicality, it may not give much difference when whether you take MLSS or MLVSS. But in reality, what the thing is, MLVS represents the organic fraction of MLSS, which is undergoing the biological decomposition. So always better to take the value of MLVSS rather than MLSS. All the terms are same, and those things will be understood when a couple of numericals are considered for design of these activated sludge processes.